Imagine a major fintech platform in 2026, processing millions of transactions per second while simultaneously powering thousands of autonomous AI agents for fraud detection and portfolio rebalancing. Suddenly, a minor latency spike in a downstream KYC service triggers a catastrophic chain reaction. This is the cascading failure, a classic nightmare in synchronous architectures. Even with advanced service mesh and circuit breakers, the sheer volume of API sprawl creates a death star of dependencies. When service awaits for service B, which is waiting for service C, resources like thread pools and TCP connections are exhausted in milliseconds. The system doesn't just slow down, it collapses under its own weight because it's built on the assumption that the world will wait for a response. We are witnessing the silent death of the request-response paradigm in the face of unpredictable, high-velocity AI traffic. This isn't just a scaling issue, it's a fundamental architectural flaw that triggers a domino effect by the end of this lecture. Moving into 2026, the traditional concept of data, at rest storing information in a database and querying it later, is becoming an architectural bottleneck. Modern systems require intelligence in motion. This means moving from a passive request-response model to an active, event-driven runtime where the AI agent doesn't wait for a user to click a button. It reacts to the state of the world as it flows through the system. We are talking about event-time processing and stateful stream processing, where the event log is the source of truth. In this new world, tools like Kafka and Flink serve as the central nervous system, processing data at the moment of birth rather than the moment of storage. Transitioning from synchronous to asynchronous isn't just a technical upgrade, it's a fundamental change in how we perceive the flow of information. To solve this, we must stop treating events like simple messages to be consumed and start seeing them as a continuous stream of truth. A shift we will explore in the next chapter, the DNA of modern events, queue vs stream. In the world of system architecture, we often use the word message and event interchangeably, but their behavioral DNA is fundamentally different. Traditional message queues like RabbitMQ or Rita streams are built on the fire and forget principle. Once a consumer acknowledges a message, it is deleted from the queue to optimize memory. This is perfect for task distribution, but fatal for data traceability. Kafka, however, is a distributed commit log. It treats data as an immutable record that persists after consumption. In the context of 2026 enterprise architectures, this persistence transforms Kafka from a simple transport layer into a source of truth that allows multiple independent systems to view the same history at different times. Question: if data is never deleted, how does Kafka prevent a storage explosion while maintaining peak performance? We will look at retention strategies shortly. The most critical advantage of Kafka's log-based architecture is replayability. In modern AI agent runtimes, we frequently encounter scenarios where a model needs to be updated or a logic bug needs to be fixed. With a traditional queue, that historical data is gone. In Kafka, we simply reset the consumer offset and replay the stream. This ensures state recovery and consistency across distributed AI nodes. By maintaining a strict retention policy, Kafka allows us to synchronize the state of a digital twin or an autonomous agent by reprocessing historical events. This capability is the fundamental requirement for event sourcing patterns, where the state of the system is derived from the sequence of events. Teaser, but simply storing events isn't enough. We need to scale this across thousands of consumers without losing the order of operations. Looking at the evolution of messaging, we have moved from simple request-response models to the central nervous system of the enterprise. In the early 2010s, PubSub was about simple notifications. Today, it is about data integration. In the 2026 landscape, Kafka is no longer just a buffer between services. It is the integration backbone where streaming ETL, real-time analytics, and AI inference coexist. This shift from messaging to streaming means that the data is alive and moving. We no longer wait for a batch job to run at midnight. The event itself triggers the logic as it flows through the nervous system. Payoff: this sounds like a lot of overhead, but Kafka's internal mechanism is surprisingly lean, relying on a few core concepts to achieve massive scale. To understand how Kafka scales, we must master the triad of partitions, offsets, and replication. A topic is not a single entity. It is divided into multiple partitions spread across different brokers. This is the unit of parallelism. When you write a message, it is assigned an offset, a unique, sequential ID within that partition. By distributing partitions across a cluster, Kafka allows multiple producers and consumers to work simultaneously. Furthermore, the replication factor ensures that even if a broker fails, the data remains available on another node. This architecture provides a strict ordering guarantee within a single partition, which is vital for maintaining transactional integrity in distributed systems. Question: but how do we handle the risk of duplicating data during network retrieves? The answer lies in the exactly once semantics. In a distributed environment, the exactly once delivery guarantee was once considered the holy grail. Kafka achieves this through a combination of idempotent producers and transactional APIs. An idempotent producer assigns a unique producer ID and sequence number to every message. If a broker receives a duplicate message due to a retree, it simply discards it. For cross-partition consistency, Kafka's transactional coordinator ensures that a group of messages is either all committed or all aborted. This is non-negotiable for 2026 AI workflows where a single event might trigger multiple downstream actions, like updating a vector database and sending a user notification. Payoff: while these features ensure correctness, they would be useless without the underlying hardware-level speed that makes Kafka famous. The secret to Kafka's throughput isn't complex software, it's how it leverages the operating system. Kafka uses a zero-copy approach. Instead of copying data between kernel space and user space multiple times, it uses the sendFile system call to move data directly from the disk cache to the network card. Furthermore, Kafka treats the OS page cache as its primary buffer. By using a linear disk I/O pattern, Kafka achieves speeds that rival random access memory while maintaining the durability of a disk. This low-level optimization allows Kafka to handle millions of events per second with minimal CPU overhead. Question: now that we have a high-speed, reliable stream of events, how do we perform complex, stateful calculations on that data in real time? That's where Apache Flink enters the stage. In the traditional database paradigm, data is at rest. We write it to a table and then run queries against it. But in the 2026 architecture, this is too slow. Apache Flink flips this script through streaming SQL and dynamic tables. Instead of the query being temporary and the data being permanent, the query is permanent and the data is a continuous stream of changes. Imagine a stock price feed. Flink treats this stream as a table that is constantly being updated in real time. This is not just a view, it is a live computation engine that pushes results the moment an event occurs. For an architect, this means moving from a pull model to a push model of intelligence. We are no longer asking what happened, but rather defining what should happen right now as this event arrives. This fundamental shift allows us to build systems that react with sub-millisecond latency. But as we move from static tables to dynamic streams, we encounter a massive challenge: the chaos of time. How do we handle events that arrive out of order? That is where the concept of temporal logic becomes critical. In a distributed system, event time is rarely the same as processing time. Network delays and system throttles mean events arrive late or out of order. Flink solves this using windows and watermarks. Think of windows as buckets of time-tumbling windows for fixed intervals or sliding windows for overlapping views, but the real magic is the watermark. A watermark is a heuristic signal that tells Flink we expect no more events older than this timestamp. It allows the system to make progress even when the data is messy. If a late event arrives after the watermark has passed, Flink can either drop it or route it to a side output for specialized handling. This level of temporal control is what separates a simple message consumer from a true stream processor. In high-frequency trading or real-time fraud detection, missing the timing means missing the truth. But this brings up a haunting question. If the system crashes while holding all this temporal state in memory, does everything vanish? The answer lies in Flink's legendary fault tolerance mechanism. To provide exactly once processing semantics, Flink uses a distributed snapshot mechanism called checkpointing. Based on the Chendi-Lamport algorithm, Flink periodically takes a consistent snapshot of the entire application state, including the current offset in Kafka and the internal state of every window. These snapshots are stored in distributed storage like S3 or HDFS. If a node fails, Flink simply rolls back to the last successful checkpoint and resumes processing without duplicating or losing a single event. SavePoints take this further. They are manually triggered snapshots that allow you to stop a job, update your code, and restart from the exact same state. This is the enterprise-grade DNA of Flink. It provides the reliability of a database with the speed of a stream. This capability is essential because as we moved AI agent runtimes, the state is no longer just a counter, it is the memory of the agent itself. But where does this massive amount of state live physically during execution? Let's look under the hood at the state back in architecture. In Flink, state isn't just an afterthought, it is a first-class citizen. For small workloads, state can live in the JVM heap, but for high-scale enterprise applications, we use the RocksDB state backend. RocksDB allows Flink to maintain terabytes of state locally on the task manager's disk, using an LSM tree structure for high-performance writes. This local state strategy is the secret to Flink's performance. By keeping the state close to the computation, we avoid the data locality tax of constantly calling an external database like Redis for every single event. Think of it as a cache that never expires and is always consistent. When you compare this to traditional architectures where the application is stateless and the database is the bottleneck, the Flink approach is revolutionary. It allows for complex aggregations and historical lookups at the speed of RAM. But storing state is only half the battle. Can we use this state to build complex, interactive logic that looks more like a microservice than a data pipeline? As we head toward 2026, the line between data processing and application logic is blurring. This is perfectly exemplified by stateful functions. Stateful functions, statefun, is an abstraction on Flink that allows developers to build distributed applications that look like serverless functions but possess consistent, local state. Each function has its own private state, and functions communicate by sending messages to each other through Flink's streaming backbone. This solves the greatest weakness of traditional FOSS, the stateless problem. In a statefun architecture, the state moves with the message, ensuring that when an AI agent receives a prompt, it already has access to its context memory without a database round trip. We are effectively building a logical mesh of intelligence. This is a radical departure from the request-response microservices we've built for the last decade. But wait, some might argue, why not just use Spark Streaming for this? It's a valid question with a very specific answer when we talk about AI latency. When choosing a streaming engine for 2026 AI requirements, the distinction between Flink and Spark Streaming is vital. Spark Streaming is essentially micro-batching. It collects events for a few seconds and then processes them as a batch. This introduces a floor on latency that is often too high for interactive AI agents. Flink, on the other hand, is a native streaming engine. It processes every single record the moment it arrives. For AI agents that need to react to a user's heartbeat or a fluctuating market signal, those milliseconds matter. Flink's fine-grained state management and low-level control over time make it the superior choice for stateful intelligence. In this chapter, we've seen how Flink turns passive data into active, stateful processing. But Flink is just the engine. In the next chapter, we will see the cockpit, how these streams and states converge to create the 2026 frontier, the AI agent runtimes. By 2026, the industry has realized that large language models are not just chat interfaces, but the CPU of a new kind of software. However, a CPU without a robust runtime is useless. This is where Apache Flink evolves from a data processor into an AI agent runtime. In traditional architectures, AI agents suffer from context drift and high latency due to request-response bottlenecks. By utilizing Flink as the execution layer, we allow agents to consume event streams natively. This means the agent doesn't wait for a user to ask a question. It lives within the stream, processing events as they occur and maintaining complex state across multiple interactions. We are moving away from stateless inference towards stateful, autonomous execution, where Flink manages the agent's working memory with millisecond precision. This transition is critical for enterprise-grade AI that must act autonomously in high-stakes environments. But how does an agent actually maintain a coherent thought process across millions of concurrent streams? Teaser, the answer lies in how we redefine memory through the lens of Kafka and Flink. To build a truly intelligent agent, we need to solve the memory problem. In the 2026 architecture, Kafka serves as the short-term episodic memory, a high-speed log of everything the agent has seen and done. Flink acts as the reasoning loop, pulling these memories and transforming them into decisions via semantic triggers. Unlike traditional triggers based on fixed rules, semantic triggers use vector embeddings to identify patterns in the stream that require agent intervention. For example, if a sequence of transaction events deviates semantically from a user's historical behavior, the Flink agent triggers a reasoning cycle to investigate. This loop of observe, orient, decide, act happens entirely within the streaming fabric. We use vector streams where raw data is converted into high-dimensional embeddings in real time, allowing agents to perform semantic searches over the last few minutes of activity. This architecture ensures that the agent's reasoning is always grounded in the most recent evidence. Question: but is current memory enough for complex decision-making, or do we need deeper context injection? Real-time retrieval augmented generation, or real-time RAG, is the final piece of the streaming agent puzzle. In 2026, we don't just query a static vector database. We perform context injection by merging live event streams with historical data. Flink manages this by maintaining a temporal context window. When an agent needs to make a hyper-personalized decision such as adjusting a dynamic price or intervening in a complex logistical chain, it doesn't just look at the current event. It looks at the enriched stream where Flink has already joined the event with relevant user profiles and real-time market conditions. This dynamic prompt engineering occurs at the infrastructure level, where the system assembles the perfect prompt with zero-day context before it even reaches the LLM. This reduces hallucinations because the model is always provided with the ground truth of the current state of the system. Payoff: this represents the pinnacle of the stack we've discussed, but it creates a massive divide between how we handle raw events and the intelligence we derive from them. As we generate vast amounts of derived state from our AI agents, we face a storage challenge. We cannot keep everything in Kafka forever, yet AI models need this data for long-term self-correction and training. Enter the streaming lakehouse, primarily using Apache Iceberg. By 2026, the boundary between a stream and a table has blurred into a single architectural entity. Raw events flow from Kafka into Iceberg tables via Flink, while the derived state, the reasoning, the decisions, and the outcomes is stored alongside them. This allows data scientists to compare what the AI thought, the derived state, versus what actually happened, the raw events. This comparison is the foundation for reinforcement learning from human and machine feedback. We are no longer just storing data, we are storing the history of intelligence within our enterprise. Question: if the AI is the one reading this state and making decisions, what happens to our traditional architectural patterns like CQRS? In an AI-centric world, the classic CQRS pattern undergoes a radical transformation. Command query responsibility segregation used to be about separating writes from reads for UI performance. In 2026, the read model is no longer just for a human looking at a dashboard. It is an autonomous agent. The agent observes the materialized view of the world created by Flink and emits new commands back into the system. This creates a recursive event sourcing loop, where every AI decision is an event, and the state of the agent itself is sourced from the history of its own decisions. This is vital for AI explainability. When a regulator asks why an agent made a specific decision, we don't look at a black box log. We replay the event stream to see exactly what state the agent was in and what events triggered its reasoning. Payoff, this isn't just theory, it's how the most resilient autonomous systems are being built right now. The ultimate realization of this architecture is the self-correction feedback loop. In this 2026 model, we deploy critic agents alongside worker agents within Flink. When a worker agent emits an event representing an action, say, an automated purchase, the critic agent intercepts it on a Kafka topic. It performs a secondary reasoning task to validate the action against enterprise constraints and safety boundaries. If the critic detects an anomaly, it emits a correction event that Flink uses to update the system state and trigger a rollback or a secondary negotiation. This closed-loop system allows AI to learn from its own mistakes in real time without human intervention for every minor error. We have moved from simple event processing to a streaming nervous system that is self-aware and self-healing. Bridge, now that we understand the technical how of these AI runtimes, the final question is, how do we actually deploy this at scale and position it strategically within an enterprise? We'll answer that in our final chapter on enterprise deployment. Transitioning to a real-time AI enterprise in 2026 requires more than just code. It requires a strategic choice in infrastructure. When building a streaming architecture, the first crossroad is deciding between a self-managed vanilla Kafka setup or a fully managed ecosystem like Confluent Cloud or Avon. In a technical landscape where AI agent runtimes require sub-millisecond response times, the operational burden of managing zookeeper-less craft clusters or Flink state backends manually can lead to catastrophic technical debt. For most enterprise-scale deployments, the focus has shifted towards serverless streaming where the infrastructure scales elastically based on throughput. We must evaluate the total cost of ownership not just by the cloud bill, but by the reliability of the event mesh that feeds our agents. A hybrid cloud approach is often the reality, where sensitive data remains on-premise while the heavy-duty Flink processing happens in the cloud. Choosing the right stack is about balancing the sovereignty of your data with the velocity of your innovation. But selecting the platform is only half the battle. How do you protect the data these agents consume? In an era where autonomous AI agents can read and write to your live event streams, security and governance are no longer optional add-ons, they are the foundation. We are moving beyond simple TLS and SASL authentication. We now require event-level governance where data lineage must be tracked across every transformation step. If an AI agent makes a financial decision based on a stream of events, you must be able to audit exactly which event version triggered that logic. This requires integrated schema registries and metadata management that track the flow of information from source to sink. Furthermore, role-based access control, RBAC, must evolve into context-aware access control where permissions are granted based on the agent's current task and the sensitivity of the data topic. Implementing a zero-trust architecture within your Kafka clusters is the only way to prevent a single compromised agent from poisoning your entire data lake. If you think security is complex, wait until you see these components working in a high-stakes logistics environment. Let's examine a real-world case study, an autonomous supply chain system deployed in 2026. In this architecture, thousands of IoT sensors feed real-time logistics data into a global Kafka cluster. Apache Flink serves as the brain, performing complex window joins between weather data, traffic patterns, and inventory levels. When a disruption occurs, a Flink job identifies the pattern and triggers an AI agent runtime. The agent doesn't just send an alert, it analyzes the stream, consults a RAG-based knowledge base of vendor contracts, and executes a rerouting command back into the Kafka command topic. This creates a closed-loop system where the delay between event and action is reduced from hours to milliseconds. The strategic positioning here is sense, think, act at scale. By treating every business event as a trigger for potential autonomous action, companies are moving from reactive dashboards to proactive intelligence. Architectural beauty is fine, but how do we prove to the board that this multi-million-dollar transition was worth it? Measuring the success of a streaming AI transition requires a shift in how we define ROI. Traditional metrics like system uptime are necessary but insufficient. In 2026, we measure decision latency, the time elapsed from an event occurring to an AI agent taking a valid action. We also look at data freshness for our RAG systems. If your AI agent is reasoning based on 10-minute-old data, it is essentially hallucinating in a past reality. A common pitfall is over-engineering for latency, implementing sub-second Flink jobs where a 5-second window would suffice for a human-in-the-loop process. Expert strategic positioning means identifying which business processes truly benefit from real-time intelligence and which are better served by traditional batch windows. Success is found where streaming architecture reduces the cost of errors by catching them as they happen. We've built the engine and secured the perimeter, but where is the entire industry heading? Let's wrap up with the final vision. The future is a stream. As we reach the conclusion of our journey, we must synthesize the strategic roadmap for 2026. We began by debunking the myth of Kafka as a simple message queue, evolving it into the backbone of a streaming AI agent runtime. The key takeaway is the convergence of 3 pillars: real-time event ingestion with Kafka, stateful processing with Flink, and persistent intelligence with AI agents. This architecture eliminates the data gravity problem by bringing compute to the data in motion. In the coming year, we will see the rise of the stream-native data lake through Apache Iceberg integration, allowing a single source of truth for both real-time analytics and historical training. This shift from store-then processes to process while moving is the fundamental architectural reversal of our time. But how do we bridge the gap between these high-level concepts and your current legacy infrastructure? Let's look at the final call to action for every architect in this room. My final strategic insight for you is this: stop building static databases and start building ecosystems of intelligence. In the 2026 landscape, data that sits idle is a liability, not an asset. The autonomous enterprise requires a central nervous system where every event triggers an immediate, intelligent response. By positioning Kafka and Flink as your AI agent runtime, you are creating a platform capable of sub-second decision-making at a global scale. This is not merely about replacing legacy systems. It is about building a foundation that treats time as a first-class citizen. Move away from the batch-first mindset and embrace a stream-first to minimize the action gap between data birth and business value. This concludes our deep dive into the reversal of Kafka's role in the modern stack. Remember, the future isn't a destination we reach, it's a stream we enter. Are you ready to stop capturing history and start orchestrating the present? Your journey into the stream starts with the very first event you process today.